amazing. If you want to become a hacker or learn Linux or get into IT, or if you're just a... Now, I'm not sure if you knew this, but there are... Now, I'm not sure if you knew this, but there are roughly 4.3 billion possible IP addresses, and we're out. Like, we don't have any more. Which is a huge problem because, as you saw in our last video, if a device wants to communicate on the internet or with other devices, it needs an IP address. So in this video, I want to talk about how is that even possible, right? Because the people who invented the internet were pretty stinking smart. But you see, around the time they invented it, which the internet's birthday is officially January 1st, 1983, it seemed like the 4.3 billion supply of IP addresses was inexhaustible, right? I mean, it sounds like it might be. But they didn't understand two big things that honestly they probably couldn't see coming. The internet became kind of a big deal, obviously, right? And second, they did not anticipate all the devices that we would assign IP addresses to. I mean, think about it. They're like, oh yeah, maybe a few computers here and there. No, your watch, your oven, your microwave, your toilet. Now, because they did not understand these two things would happen, they did some pretty stinking dumb things. They mismanaged the heck out of our IP address space. So in this video, we're gonna explore that. What did they do? And later, we'll talk about how we fixed it, kind of, with the Band-Aid. So, by the end of this video, not only will you understand why the inventors of the internet were very terrible planners, you'll also understand a lot about IP addresses. We're building on the foundation that we set in the first video, and this video will prepare you to become a Master Chief Ninja, Subnetting Skill Master Chief Ninja, because it is part of my series, You Suck at Subnetting, so make sure you catch all the episodes. Anyways, now real quick, can I show you something? Right back here. This guy right here. That little Raspberry Pi is running an entire business phone system. It's called 3CX, it's amazing, and it's a sponsor of today's video. Now, you may remember me doing a video on setting up 3CX on a Raspberry Pi billion IP addresses. And if you want to get nerdy, it's actually 2 to the 32nd power, which is actually 4,294,967,296 IP addresses. But you know, 4.3 billion, close enough. So here's what they did, and it comes down to how they organize the IP addresses. They put them into what are called classes, A, B, C, D, E. Yeah, that's it. A, B, C, D, E. And there are two problems I have with this. First, there are large groups of IP addresses that we can't even use. I know, like why? You'll see. And second, they set it up to where they gave away too many IP addresses. Because again, they didn't expect the internet to take off and so many devices to have IP addresses, so they gave big companies just, hey, why don't you take 16 million IP addresses, just take them. Well, we don't care, we have so many right now, we'll never run out. Idiots. Anyways, here's what they did. So you may recall from the first video that an IP address is 4 numbers separated by 3 dots. And each of these numbers can be anything between 0 and 255, which, using big brain math, will give you a total of, well, right up here. See the top, 4.3 billion IP addresses. But man, did they screw it up. So here's the classes. Here's how they organize these IP addresses. So here's the chart. Here's how we group them. I'm not gonna list every one of them off. That would be super boring. So just look at it. You can read. But seriously, if you're studying for an exam where you have to know subnetting and the classes, then you might want to make flashcards out of this and memorize it. Now, at first glance, there's nothing wrong with this. Actually, there is one big glaring problem with it between A and B. See if you can notice it. We'll talk about that here in a second. But the problem doesn't come in until this very weird thing they did. Here it comes. You ready? The subnet mask. Classes A, B, and C each have their own default subnet mask, which, if you recall from our last video, it determines basically how big the network is, or which numbers in our IP address stay the same and which ones change. For example, let's take the first network we have here. In class A, we have the 1.0.0.0 network. This is how it would look over here. Let's draw it out. There's the IP, and here is the subnet mask. If you remember the hack I talked about, when you see a 255 in the subnet mask, the corresponding or matched up octet, which is the first one here and the first one here, will stay the same. So 1 will always be in the IP address. And when you see a 0, anyone's game. It can be any number between 0 and 255. Now, that is a pretty stinking big network. Because if we're just keeping the first octet the same, the 1, but everything else can be different, do you know how many addresses that is? That is, I gotta look it up. Oh my goodness, 16,777,214 IP addresses in one network, which is insane, especially when you contrast that with your home network, which we talked about in the first video, might look like this. There's the IP address, and here's the subnet mask. And with 3255s, we're locking in those first 3 numbers, leaving the last one, the last octet, to be anything, which with this is a humble 256 addresses. So 256 versus 16 million, why? Well, the idea was that government entities or big companies might need a lot of IP addresses. And since they had plenty, 4.3 billion, let's just give them a whole bunch. And that's what the Class A was for. And you might recognize some of the companies that have these Class A IP address networks, like General Electric, GE. They own 3.0.0.0. IBM has 9. AT&T has 12. Xerox, 13. HP, 15. Each of these companies owns over 16 million IP addresses. So, looking back at our Class A range, Class A networks are very host heavy because they give you so many stinking hosts. Over 16 million. And thanks to their default subnet mask, there are only 126 total Class A networks. Now you're probably thinking, Chuck, are there actually networks like that big? Like 1.0.0.0 with 255.0.0.0 as a subnet mask? That's a lot of IP addresses in one network. And the answer is no, they don't really make them that big. Yes, the governing body who hands out IP addresses, the Santa Claus of IP addresses, or the head Oprah, we call them IANA or IANA, the Internet Assigned Numbers Authority. They will assign or allocate all those IP addresses, that entire network, to a company. We'll pick on IBM for a second with their 9 network. What they will do is take this huge network full of IP addresses and cut it up into smaller slices. So they might have the network 9.1.4.0 with a subnet mask of 255.255.255.0. And you're probably thinking, whoa, they can do that? Yeah. So while a Class A network has the default subnet mask of 255.0.0.0, that's the minimum they have to have. They can cut it up very small and say in this network, the 9, the 1, and the 4 will always be an IP address, and this particular network is smaller with 256 addresses. So they can take their big, massive network and turn it into smaller subnetworks. And that, my friends, is your first little glance into subnetting, which is what we're gonna really cover and dive deep into in the coming videos. Oh, and by the way, also, what we did here, taking a Class A network, and we cut it up and made it smaller with a different subnet mask other than its default. We call that a classless network. So for example, my home network is actually 10.7.1.0, a Class A IP address or a Class A network, but my subnet mask is 255.255.255.0, making it a degenerate, a classless network, because we're breaking all the rules. We're not obeying this A, B, C, D, E, F, G stuff. That's basically what you're doing. Got no class. But if you do obey the rules and you use the default subnet mask, then you're class full. You're full of class. You're elegant, but you're no fun. No, I'm just kidding. A little bit. So anyways, getting back to our address ranges, our classes. We focused a lot on Class A right here, and his subnet mask giving a network just a ton of IP addresses, too many. Way too many, which is, again, is part of the problem I have with IANA or the head Oprah. They just gave away too many IP addresses. And then as we move down, you'll notice that Class B has a different default subnet mask of 255.255.0.0. So again, if we take this first network right here, bring it on down here, it might look like this with a subnet mask of 255.255.0.0. Locking in those first two numbers, those first two octets, those will always stay the same. But then these last two numbers, these last two octets can be anything they want between 0 and 255. I'm talking 65,534 hosts or IP addresses per network. So bummer, you get less IP addresses, which again is way too many, but the flip side is that you get more networks with a Class B. IANA or Queen Oprah can assign 16,382 networks because again, a Class B by default must have a minimum of a subnet mask like this. And then moving on down the line, we got Class C, which will look the most familiar to you, right? Because it contains your home network. And again, we'll take that first network here, bring it on over here. Come on, little guy, with this default subnet mask. And those first 3 numbers, they're locked in. Can't touch those octets. And looking very familiar, we have a total of 254 available IP addresses on that network. This is the best plan. They should have done this with every single network because with Class C networks, we have a total available for Queen Oprah to assign 2,097,150 networks. So if they had done that with every class, we'd be okay. Kind of, maybe. No, we wouldn't. We have a different solution for that because eventually we would have run out. But we wouldn't have run out so quickly. Come on. Inventors of the internet, why can't you just look into the future and anticipate our needs? Seriously. So that's Class A, B, and C. We're about to get to the D and E, which infuriate me. I mean, I don't get too angry about it, but it's still pretty stupid. But first, I just want to point out, and hope that you're picking up, that the job of the subnet mask is to help us determine how many networks and how many hosts we have for each class. Class C gives us the most networks and smaller hosts per network, whereas Class A gives us too many freaking hosts per network and like only 126 networks if you stuck with the, classful subnetting or classful networks. But of course, and you probably assume this, nowadays, we mainly do classless networks to take advantage of the IP addresses we need to use. So anyways, I'm gonna officially say, IANA, that was a dumb idea. And now we're stuck with your mistake. But it's okay. All we have to worry about is learning this chart, memorizing it, knowing what it is, and then learning something scary called IPv6. We'll cover that later. So now let's talk about my biggest problem with this, is that there are IP addresses that we cannot use. We just can't. We can't. So Class D and E, notice they don't have a subnet mask because it doesn't matter. Class D IP addresses are reserved for multicast, or you might see it written in one word. I never know. All you have to know about those is that they're very important to networking and you can't use them right now. So don't worry about it. Just memorize what they are. And then Class E networks, these bad boys are mysterious. They are locked up in the Department of Mysteries, FBI, CIA, I don't know. They are experimental. So don't even think about touching those. Whew, you'll get in trouble. And I'm just kidding. You can't touch them. They're untouchable. Anyways, so we can't use D&E. And there's one more. I don't know if you noticed this. Look at that chart. Is there a number range missing? Can you find where's Waldo? I'll give you a hint. It's in between A and B. And also, here's the other hint, Dorothy, because there's no place like home. This will make sense. I promise it'll make sense here in a bit. I'm not losing my mind. You may have noticed that the range here ends at 126 and then picks back up in B at 128, making us go, huh, where the junk is 127? Like, where'd it go? That's a lot of IP addresses just missing. That's an entire Class A network, which means we're talking 127.0.0.0 with the subnet mask 255.0.0.0, which leaves missing over 16 million addresses. Where are you guys at? You know where they are? They're on your devices. These range of addresses, anything beginning with 127, are what's known as loopback addresses. You may have heard that term before. They're used for network testing. Now don't get me wrong, I love me a good loopback address because you can use it to test your network. You can actually make sure that your computer's networking is working by pinging your loopback address. What am I talking about? Let's try it real quick. If you're on Windows, go ahead and launch your command prompt or type in Windows key search CMD. It'll look like this. On Mac and Linux, it'll be terminal. And right here, stand across the board, type in PING or ping space 127.0.0.1. Now, if you're like, what the junk is ping? Ping is what we use in IT to see if something is alive and awake. So for example, I, on my computer, might send a ping message out to networkchuck.com saying, hey, are you awake? And if networkchuck.com is awake and alive and actually there and living, he should respond back with a response. It is by far the most common troubleshooting tool you'll ever use in IT. So looking back at our example here, we're gonna ping 127.0.0.1, which is an IP address that just is virtual and lives on your computer. And we should all get the same result if you're working. Hit enter. Hey, are you awake? Yes, I'm awake. Hey, are you awake? Yes, I'm awake. That's essentially what you're doing. You're just making sure that you can hear yourself. But the kicker is, and it's so stinking stupid. Maybe, is there something I don't know about this? Here's the problem. I think all we needed was just this one IP address, 127.0.0.1, to test our NIC, our network, to make sure it's working, because we just did that. But for some reason, they thought we might need 16 million to do that. Because, do this. You can go ping 127.145.145.8. Just a random address, and we get the same thing. We're pinging ourselves. Our computer has 16 million virtual IP addresses ready to respond to itself. Why? Okay, it's okay, Chuck, it's okay. So, roughly 4.3 billion IP addresses, and we can't use a lot of them, and a lot of them were mismanaged. Thanks a lot, Ayanna. Thanks a lot, Head Oprah. No, it's fine. It's fun to learn this. It's fun to learn how our IP addresses were formed, how they're organized into classes A, B, C, D, E, and it's definitely something you want to commit to memory. So get those flashcards out. Memorize this sucker. It will come in handy your entire IT career, and also pretty handy on any kind of test you might be taking here soon. Now I know this might all seem like doom and gloom. I identified some problems that we have with our current IP address space and why we are just out. We're done. But don't worry, in the coming episode, I'll show you the massive band-aid we put on our IP address situation, and it did solve the problem. Kind of. And then we put an even bigger band-aid on it to really solve the problem, but who knows what will happen. I know, I'm not being specific, because I really want you to watch that video, so go ahead and watch it. It should be up here somewhere, or maybe up next over here or over here. I never know where to point. Anyways, that's all I have. It's 1996 and the internet is going to end. It's doomed, we're out of IP addresses, there's nothing we can do. But then in comes in RFC 1918, an unlikely hero that literally saved the day. Without it, we would not have the internet we have. You wouldn't be watching me right now, and my toilet could not be connected to the internet. Which I think is I don't know, a bad thing? But seriously, we're talking about two things in this video: private IP addresses and NAT. Without these two things, we would be nowhere. And they literally changed the game of the entire internet, the entire world. So get your coffee ready. Let's jump into this. Whoa, hold up. Before we dive in, I gotta tell you, not only do you suck at subnetting, you also probably suck at password security, which means you're gonna get hacked, like any day now, any moment now, like now. You should check your passwords. You just got hacked. See, I told you. But if you're using a password manager like Dashlane, then you're probably okay. Dashlane is a sponsor of this video, and I am legit a customer. I use them personally for all my passwords, and more importantly, I use them in my business to protect me from my employees. Because they're not the most tech savvy in the world and would use password 123 for everything if I let them. Is that you? Don't do that. You know who you are. But with Dashlane, I can force them to be secure with two-factor secure cards. So quickly buy notes and secrets they have are probably for sale on it right now. Dark web, they monitor all. You use one, and I can highly recommend Dashlane. Now I feel safe enough to dive into the video. Let's do this. Welcome back to our You Suck at Subnetting series, where I want to teach you how to become a Master Chief Ninja Subnetting Master something. You're gonna become really good at subnetting. That's what I'm talking about. In the last few episodes, we covered, hey, what's an IP address? And hey, we only have 4.3 billion of them about. And hey, the designers of the internet organized them terribly, and now we're almost out of IP addresses. Actually, we are out of IP addresses. But we did something. RFC 1918. Let's talk about it. RFC 1918 was the internet's giant band-aid. And the band-aid was private IP addresses. Now, so far, we've focused on these guys right here, what we'll refer to now as public IP addresses. Or basically IP addresses that can be reached on the internet. Which when you think about the internet, I want you to think about it as just a big network. Just a bunch of devices all connected together. And everything that wants to talk on that big network needs an IP address, a public IP address. So you, sitting there on your computer, you do need a public IP address to watch this video. Or maybe on your phone, whatever. You still need a public IP address to interface with the internet. But it has to be unique, so if you have 128.1.4.43, David Bombal down here cannot have that same IP address. They have to be unique. It'd be like us having the same cell phone number. You try to call it and we both get the ring. It just wouldn't work, right? You can't both have the same cell phone number, and you can't both have the same public IP address. But going back to our problem, there aren't enough IP addresses to give everyone and every device a public IP address. If I just think about all the devices in my house, I know I at least have, and I'm probably being conservative, 70 or so devices with an IP address. No, I've got more than that. Over 200 devices in my home have an IP address. And if every home was like me, that'd be crazy. So the powers that be created private IP addresses. And actually what they did is they took a few chunks out of our public IP address ranges and just said, hey, these are private now. You can't use them anymore. That's legit what they did, so check this out. They did an IP address transplant out of each of these classes, A, B, and C. Took a nice little chunk and said, bam, private IP addresses. And just like their classical counterparts, they have the same default subnet mask. And look at this, you might have caught this. That Class C IP address range might look kind of familiar, right? And that's how I knew it was your home network, because the most common private IP address range that routers use, home routers, is 192.168, a Class C IP address range. So your home network, 192.168.1.0, with this subnet mask. I knew you had it because, well, everyone has it. Which means that private IP addresses by nature are not unique, contrary to their public IP address counterparts. Which, hey, solves our problem because, man, if I can have the same network as you and David Bombal and my brother Cameron, then we don't have a problem anymore. We can all share the same IP addresses. Right? Well, no, we still have one problem. These private IP addresses will not connect you to the internet. And that's the big difference between public and private. Private IP addresses, those ranges, are not publicly routable on the internet, which means you can't talk to them from the internet. So right now with your computer, it has a private IP address. Check. Do that IP config thing we did in the first episode. You have a private IP, and you can't access the internet. You just can't. Which you're probably thinking, well, Chuck, you're wrong. I'm watching you right now. I know. And you're right. To solve that pesky internet problem is the other half of the band-aid. It's a magical thing that changed the game completely. It's called NAT, or Network Address Translation. So what's cool is that right now in your home network, NAT is doing its thing. NAT is working its magic, and here's what's happening right now. So look at your home network. This is it right here, right? You've got a smart toilet? I know you do. Don't lie to me. Here in your home network, it would be impossible to assign every device you have a public IP address. It just wouldn't work. There's not enough for everyone. So instead, we have Oprah, your router, give out private IP addresses. IP addresses that are not unique. Millions of people can have the same IP address, and it totally works. But if you wanted to go out to networkchuck.coffee, which lives on a server in the cloud somewhere, I'm not gonna tell you where it is, you just couldn't do it. You wouldn't make it past your own little private home network because networkchuck.coffee is on a server on the internet with a public IP address. And this IP address for my server is totally unique. So here's the magic. In comes Mr. Nat. Actually, first, your ISP, your internet service provider. Mine, for example, is AT&T. You say, hey, AT&T, I want my home to connect to the internet. And they say, okay, here is one public IP address, and you can borrow it. We'll let you borrow it, but just one. And you're thinking, holy crap, I have like 300 devices I have to connect. That's not enough. And I'll tell you, yes, it is. With NAT, it's more than enough. Check it out. AT&T, being the bigger Oprah, will assign your littler Oprah, your router, a public IP address. I'll just pick one randomly. Let's say 11.5.4.28. So what NAT will do, and by the way, NAT is being performed by Oprah, your router. I know, she does it all, doesn't she? Your router is doing the NAT, the network address translation. So whenever your smart toilet wants to go out to networkchuck.coffee, it, with its private IP address, will go, hey, Oprah, can I go to networkchuck.coffee? She'll say yes, I'll take care of it for you, and then she'll send a message to networkchuck.coffee, and everything's totally cool because she can communicate with my server because she has a public IP address of this guy right here. NAT will auto-magically translate that private IP address into a public one when it leaves your router. And your router, Oprah, is actually doing it. So what that means is that not just your toilet has that public IP address, but literally every device on your home network, when it accesses anything from Netflix to YouTube, it doesn't matter, their identity is one identity, that one public IP address your ISP gave you. So do you see how that kind of saved the day with our internet woes? Instead of every device in our home networks having a public IP address, so no, we're not doing that. That's crazy. Let's give them private IP addresses, and then we'll give them just one public IP. Now I want you to do something fun real quick, because right now you do have a public IP address, just one public IP in your house. If you open up your web browser, I Googled David Bomble's face earlier, and you go to Google, and I'm gonna hide mine. But if you type in, what is my IP address into Google, it'll tell you. That's your one public IP. Because as you're accessing Google, your computer or your phone or your tablet, whatever it is, Google sees you as that one public IP. But again, if you launch your command prompt and you type in ipconfig, your computer or your device's IP address is not that public one. It's a private one, like mine right here, 192.168.1.204, a private IP address. Isn't that cool? Man, that's amazing. Now, adding one more thing to that, it's even cooler, is when that website wants to send something back to your toilet when it talks to networkchuck.coffee. So let's say, for example, my toilet's like, hey, I want to see some pictures of coffee. So we send that request to the server saying, hey, show us some pictures of coffee. When networkchuck.coffee, the server, sends those pictures back, Oprah will automatically know, oh man, this picture is for toilet over here, 192.168.1.25, and forward it right on through. The process in that is much more complex than I'm describing here, and we'll dive deeper into that in my CCNA series, but man, is that stinking cool or what? And this right here literally saved the internet, and it's how nearly every network you can think of works, from everyone's home network, millions of people, and businesses. All the big businesses, they use private IP addresses in their business. All their devices have private IP addresses, and then they have public IP addresses using that. Isn't that cool? Man. Now, I do have some bad news. That even with private IP addressing and using NAT, it didn't solve our problem because we still did run out of IPv4 addresses. And now you notice I said something weird this time. I said IPv4. What? What are you talking about, Chuck? Yeah, okay, check this out. In this series, we are laser focusing on IPv4 addresses. You may remember earlier on I said, hey, ignore that V4. Pay attention real quick and then ignore it again. IPv4 is the typical 4 numbers separated by 3 dots. But, you know, we ran out, even with our awesome band-aids. So up came this amazing thing called IPv6. It's so amazing that we skipped 5. It's like the iPhone 10, man. And here's what an IPv6 address looks like. Dude, it's freaking nuts. It's got numbers, it's got letters, it's got extra dots on top of the other dots, colons, but it's crazy, and it's obviously much bigger. This right here does solve our problems for the time being, as far as we can look into the future. I'm afraid we might make the same mistakes. Now, the amount of IPv6 addresses that are possible is kind of insane. It's 2 to the 128th power, which if you recall from IPv4, that was 2 to the 32nd power. Second power. I don't know why I can't say that. So it's a lot bigger, so big that literally every device we have could get an IPv6 public address and connect to the internet, and we'd have plenty left over. And also you may have wondered, like, hey, what about my cell phone? Because everyone pretty much has a cell phone now, right? I don't know why this cell phone's so fat, it's like a picture frame, sorry. Let me label it. So you have a cell phone, and when you're walking around, not at your home network, not connected to Wi-Fi, you're connected to your cellular provider. And guess what? Your phone has a public IP address. So everyone who has a phone who's walking around has a public IP address. And I'm willing to bet, more often than not, your phone has a public IPv6 address. Many of the carriers out there, from AT&T to Bell to Orange, all of them out there, they're using IPv6. And yeah, that means the industry, the internet, is shifting over to IPv6. Now, sure, plenty of websites, and most of them, I would imagine right now, still use IPv4. IPv4 is going nowhere, so yes, you still need to learn it. Hopefully what you're learning here will still be valuable for at least the next 50 years. I'm calling it. But that does also mean that you will need to learn eventually IPv6. And in the course of my CCNA series, I am going to cover IPv6. And yeah, I'm not going to lie, this sucker looks scary. But don't worry, we'll take care of it later. That's for future use problem, right? Whew, man, take yourself a coffee break. This was a lot. So not only do we have different classes of IP addresses, A, B, C, D, and E, but also we have public and then private IP addresses. Public being the IP addresses that are routable on the internet. If you want to connect to the internet, you gotta have one of those guys. But then we have private IP addresses, addresses that are not unique, that most home network devices have, and they saved the internet. So your device right now you're watching me on has a private IP address. And with the magic of NAT, you can connect to the internet and watch this video. It's really crazy, really fascinating, and by the way, if you want to dive deeper into all that, we're gonna go deeper into that. But for now, in this series, we're gonna be laser focused coming up on IPv4 addresses and subnetting. Again, as I've mentioned before, it's a crazy, crazy valuable skill that you will need, and you'll need it for pretty much every discipline in IT. So buckle your seatbelt and just take one more sip of coffee. And also make sure, and I don't know if you have, but have you hacked the YouTube algorithm today? Let's make sure you do. Hit that like button, notification bell, comment, subscribe. We gotta hack YouTube today, ethically, of course. Now real quick before you leave, are you working on your CCNA, or maybe your CCNP, Security Plus, or really any IT certification? Are you working on something like that? If you are, you need Boson software. Like, I'm not kidding. They are the industry standard, the gold standard. Did I say gold? Gold. Okay, this is gonna break your brain just a little bit, but this right here, is an IP address. What? Yeah, no, it is. But you're probably thinking, Chuck, no, IP addresses look like this. And sure, you're right. But this right here is how your computer, how all computers see your IP address. It's like putting on some special glasses and seeing the code in the matrix. This is your IP address in the matrix. So, get your coffee ready. We're about to get jacked in to the matrix. That's how you say it, right? Yeah, let's go. So here is an IP address. This might be your IP address. And if you watch the previous episodes in this series, this looks familiar. This is nice and fuzzy. 4 numbers, 4 octets, separated by 3 dots. But then we just put on our matrix glasses. We're seeing this IP address in computer code. This is referred to as binary, the language of computers. Now, if we look back to the previous version, let me switch it back. This we refer to as decimal, and this as binary. Our goal in this video is to understand first what the junk is happening with this binary. What even is this? And second, we're gonna learn the magic. What I just showed you, yeah, check that out. That's cool, right? Let's do it again. You're gonna learn how to do that. We're gonna learn how to convert from decimal to binary, and then binary to decimal. Now, you're probably thinking, why? Like, why is it so important that I need to see the matrix code of my IP addresses? Well, honestly, this is kind of a wax on, wax off scenario. Learning this skill right here is going to help you do something later. This is essential to doing subnetting, because right now you suck at it, and we want to change that. So in this video, just think, this is going to help me subnet. I am going to become a decimal to binary conversion ninja. Or getting back to our analogy, you're the one. You are Neo. You can see the code going through the air. You know. So let's make that happen right now. So here we go. Take one more sip of coffee. We're gonna dive deep here. And trust me, once you learn this, it's kind of fun to do. Kind of fun. No, it's really fun. I'm gonna leave it there. But before I show you how to do this, let's talk about what's even going on here. We know this is binary, but huh? What does that even mean? Now, first, what I want you to do is count how many numbers there are here, how many digits. Go ahead and count right now. I'll wait. Pause the video. Unpause. How many were there? 25, right? No, wrong. 32. 32 numbers here, right? Or we could also say 32 bits. What does that mean? Well, you see, in computers and in the Matrix, everything has a size, right? Like this video I'm recording right now, it's 4K, it will likely be about 60 gigabytes. Right, Nick? Yeah, this picture of Bernard Hackwell is about 10 megabytes. And this text file I just created is 29 bytes. Now you probably noticed that I'm going down in size, right? Going from gigabytes to megabytes. I know I skipped kilobytes, relax. All the way down to bytes, big to small, right? You got it. But we can go even lower, even smaller than bytes. You probably saw where this is coming. We can go from bytes to bits. And that's what we're seeing here. Each of these numbers, these digits are bits. The ground floor, as low as we can go as far as size in computers goes. Go. Let me ask you a question. You might already know this. How many bits make up a byte? Pause the video. Comment below. Unpause. If you guessed 8, you're right. 8 bits make 1 byte. So if I were to ask you, how big is an IP address in bits? You might say, how many? 32 bits. And then I might ask you, hey, how big is an IP address in bytes? What would you say? 4, right? Notice how each of our octets is 8 bits. We have 4 octets at 8 bits each. 8 times 4, 32. So to sum this up, as you're looking at this binary number, what you're actually looking at is the lowest level of storage in a computer, the lowest size, the raw data. And we just discovered why we call these sections between the dots octets. Well, because octo, 8, they're 8 bits. Octo, octets. There you go, octopets, octets. I don't know why I said that. So IP addresses, 32 bits, that's cool. But now let's talk about what are these numbers even doing? Like, I don't see a lot of number diversity here. All I see are 1s and 0s. And the reason is that's just what binary is, 1s and 0s. And that's frankly all your computer cares about. 1 and 0. But it's more than just like 1 and 0. It's what the 1 and 0 are communicating to the computer. You see, 1 indicates on, and 0 indicates off. That's literally what it means. It's like a light switch. On, off, like Nosferatu. Nosferatu! Nosferatu can speak binary, and he's communicating with the computer, hey, off, on. No, on, off, Like legit, think about this. On, off, off. And by doing that, we're communicating something to the computer. And you're probably thinking, what? What is he even doing? What does on and off have to do with this number and IP addresses? This. I'm about to show you something. It's gonna get a little weird, but just hang tight with me. It will all make sense here in a moment. This is where it happens. You're about to learn how to take the matrix code of IP addresses and convert them back into decimal. We're gonna convert this IP address back to what we know and love, decimal. So here we go, coffee break. Let's get weird. I'm gonna start writing some random numbers. Hang tight with me. 1, 2, and I'm writing them backwards, right? 1, 2, 4, 8, 16, 32, 64, 128. This right here, our little chart is gonna save your life. This is our powers of 2 chart. And it's the secret sauce. It's our secret decoder ring to convert from matrix to regular stuff. Now, what do I mean by powers of 2? Well, I mean this. The first number is 2 to the power of 0. If we get our handy dandy calculator out, 2 to the power of 0 is 1. That matches. Then we have 2 to the power of 1, which is 2. Now you kind of see where I'm going with this. The next one will be 2 to the power of 2, and so on and so on. Now this will make sense here in a moment. How to build this chart. You can actually do it 2 ways. One is this way, they get the powers of 2. Start with 0. 2 to the power of 0 is 1. And go all the way until you get to 2 of the power of 7, which is 8 digits total, right? 1, 2, 3, 4, 5, 6, 7, 8. The power of 2's table. It's our secret power. Or you can just start with 1 and multiply by 2 each time. So 1 times 2 is 2. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. 16 times, you got it, right? Either way, you want to build this amazing chart right here. Why? Because watch this, the magic is about to happen. Whoa, pause. You've been working hard, you've been learning a lot, so let's take a quick coffee break and talk about today's sponsor, Safe DNS. Now, I'm not sure if you knew this, but I wasn't lying. For this next part, we're gonna bring back in Nosferatu to help us. And what I mean is we're gonna take this first octet over here and write it out. Notice how there are 8 bits or 8 numbers in our first octet, and there are also 8 numbers we wrote down in our chart. Let's match them up. So 1, 1, 0, 0, 0, 0, 0, 0. Now here we go, Nosferatu, are you ready? Remember, 1 means on, 0 means off. Here we go, the first number, 128. Is it off or on? It's on, so let's write it down. 128. The second number, 64. Is it on or off? It's on. 1 means on. Thanks, Nosferatu. 64. The rest, they're all zeros. They're off. Nosferatu, flick the light. So 0, 0, 0, 0. So none of these numbers are going to carry down. So all the rest of the numbers are off. We don't need them. Now here's what I want you to do. And this, again, still feels weird. I know. I want you to add the numbers that were on together. 128 plus 64 gives us 192. This right here, it's a big moment for you because right here, we just converted our first octet from matrix code, from binary to decimal. Legit, that's what we did. This number right here is 192 and decimal. That's kind of cool, right? Let's do our next one. Let's bring our next octet down, line up our numbers. 1, 0, 1, 0. 1, 0, 0, 0. And with the help of Nosferatu, let's see what carries over. Let's see what's turned on and what's turned off. We've got 128. Nope, no 64. 32, we got that sucker. No 16, we do have an 8. No 4, no 2, no 1. So we're left with 128 and 32 and 8. Now let's add those together. 128 plus 32 is 160, and then 160 plus 8 is 168. So the second octet in decimal is 168. Now it's starting to look familiar, isn't it? Now I'm starting to see the IP address the way we learned it. Let's do it again, but faster. Our third octet. In fact, I want you to do this by yourself. So pause the video and see if you can do this. Write this down, and with the help of Nosferatu, I know you can do it. Pause the video. Unpause. Let's walk through it real quick. Let's bring down our binary. 0, 0, 0, 0, 0. The only number that's turned on is the last one. We got ourselves a 1, and 1 plus nothing else is 1. And that's the next number in our IP address. That's what this octet means. And finally, the last one. Bring that sucker down, match up our binary to our chart. 0, 0, 0, 1, 0, 1, 0, 1. That was a lot. Nosferatu, help us out. We'll bring down our 16, bring down our 4, bring down our 1. 16 plus 4 is 20, plus 1 is 21. Guys, that's it. That's our IP address. We just converted our IP address from matrix code, from binary to decimal. How cool is that? If you don't think that's cool, I don't know what to tell you. Drink some more coffee, rewind, watch it again. Coffee's a bit cold already. I need to warm it up. Okay, now let's switch it up. Let's do it in reverse. Let's take an IP address in decimal format, the way we know and love, and let's convert that to matrix code. How do you do that? Well, with the same chart, guys. It's easy. We already have the magic decoder translation here. Here's our IP address in decimal format. Let's convert the sucker to matrix code to binary. Like always, we'll start with our first octet. We got 172 here. Now don't worry, we are still gonna use Nosferatu. He's standing by, he's ready. But it is gonna be a bit different here. So here's what we'll do. We'll bring down 172 right next to 128, and we'll say, hey, can we take 128 away from 172? Are we able to subtract 128 from 172? The answer is yeah, we can. And because we can, that means this one is on. Nosferatu, help us out. 128 is on. 1. Now for a little bit of math, we'll do it up here. 172 minus 128. A little bit of math. 12 minus 8, we got 4. 6 minus 2, we got 4. Cool. So now we have 44 left over. So 172 minus 128 is 44. We have 44 left over. So now what we'll do is we'll take this 44 over here and go, hey, can 44 have 64 taken away from it? No, it can't. So Nosferatu, help us out. 64 is going to be off. 0. And then we'll keep going down the line. Hey, can 44 have 32 taken away from it? Heck yeah, it can. It totally does. So Nosferatu, help us out. 32 is gonna be on. 44 minus 32, we got 12 left. Can we take 16 away from 12? No, right? I think you're seeing the pattern here. Nosferatu, help us out. It's gonna be turned off. We don't need 16. Let's move down the line. Can we take 8 away from 12? Heck yeah, we can. Let's do that. We got 4 left over. Oh, we forgot to make 8 on. There we go. Let's move on down the line. Can 4 have 4 taken away from it? Totally can. Nosferatu, turn it on. And then if we do our math, this one's an easy one. 4 minus 4, we got 0. And because 0 can't have 2 taken away from it or 0 taken away from it, then the last 2 bits here are gonna be turned off. 0 and 0. Thanks for the help, Nosferatu. So, what we just did, look at the bottom here. 101, 01100. We just converted the number 172 to binary. Now, I want you to try the next one. Try the next octet, which is 16. Pause the video, see what you got. Unpause. Now here, I'll walk through it real quick. You might be surprised that this one is kind of quick, because if we take 16, we go to the first one, hey, can't take 128 from it, can't take 64 from it, can't take 32 from it, so right off the bat, Nosferatu already knows, and he'll help us do this, that those have to be turned off. But when we get to 16, dude, heck yeah, we can take 16 away from 16. Let's turn that bit on. Thanks, Nosferatu. And then with some math magic, 16 minus 16, we got 0. And then going down the line, can you take 8 away from 0? No. 4, turn it off. 2, no, turn it off. 1, no, turn it off. At 16, the rest of the bits to be turned off because we can't subtract anymore, we're done. And we just converted the number 16 to binary, to matrix code. So now, go ahead, pause the video and try the next 2 octets, or the last 2 octets, 34 and 3, go. Unpause. Let's walk through it real quick. So, the third octet, we got 34. Can 128 be taken away from 34? No. 64? No. 32? Heck yeah. 34 minus 32, we got 2. So 16, 0. 8, let's turn matrix YouTube algorithm today. Let's make sure you do. Hit that like button, notification bell, comment, subscribe. You gotta hack YouTube today. Ethically, of course. Okay, here we go. Fair warning. This is not gonna be for little ears. Or if you're airing this episode to a classroom, you might wanna turn it off at this point, because we're gonna talk about something that you don't have covered yet. Now I know, you got decimal to binary and binary to decimal conversion covered, but you know what you don't have covered? Your butt, your balls, and your body. It's so awkward to say. But you know who does have it covered? Our sponsor, Manscaped. Manscaped is going beyond the groin, which is so awkward to say. With a brand new lineup of men's products called the Manscaped Ultra Premium Collection. Ultra Premium, awesome. They couldn't include any more words. The subnet mask. This is how we create the networks of the world. So when someone says, hey, I need you to take this network and break it up into a million pieces, like maybe 6 or 7 or 12, you can take these 4 steps and do it. Like, it's awesome. In fact, I want you to do it right now. Here's your homework. Instead of 4, I want you to do 5 networks. Take that same network in this video and convert it into 5. I want you to paste the answer below. The subnet mask, I want to see the regular version and cider notation, and I want to see the ranges. Let's see what you got. Now, I have good news. No matter what type of network you have, I need your help. I'm launching